Alright, this is going to be a short video, but I'm just going to run us through kind of the whole system. And I've actually already shown the propagation from a microphone, how the electromagnetic induction works, to an amplifier that uses a transformer to bring power to the amp, takes that signal and magnifies it and then sends it out to a speaker, which is the reverse effect of electromagnetic induction, to move that speaker cone to where it blasts out the sound. So now what I want to talk about is filtration. And we saw how compliance works. And if you lower the compliance, if you lower the effective mass, then you're going to get a higher resonant frequency. And so let's say that we tweak the mass and the compliance of a speaker until we have 3 speakers, and I kind of make them small, middle, and large. And this might have a natural resonant frequency of around 200 hertz. And this one of around, let's say, 2000 hertz. And maybe this one, a resonant frequency of around 7000 hertz. So how do we use those to their maximum ability? Well, what I want to do is use filters, and I want to totally reconstruct these filters. But if I look at my frequency range right here versus amplitude, I want to kind of choose those parts there, 200 hertz. And let me just say the frequency is in hertz, so I don't have to write down hertz half a dozen times. 200, maybe here at 2000, and then here at 7,000, sort of on a log scale there. So as I draw those up, I want to create, first of all, a low pass filter, one that will pass 200 hertz and then roll off. But you know what? I may also want to create it so that it rolls off above 60 hertz and gets rid of that buzz, but this is a very simple one. I might create one last high pass to put in series with this low pass to get rid of a 60 hertz signal that might happen when it's plugged in, and there's a dimmer switch with a radio frequency that interferes and makes a buzzing sound in my speakers. So annoying. Or maybe I'm missing a ground and random radio frequencies get in that are low frequency. So I'm going to send that filter to this speaker. I'm going to send that output of that filter to that speaker after I amplify it. And when I amplify this, I've got to amplify it huge. If you remember, this has to be a big signal because figure 19.3. In order to get the same sound power for a low frequency, you have to put a much greater amplitude to those signals. Have to push a much larger volume of air, and so we're going to amplify that hugely and send it to a big speaker. Next, I want to build a high pass speaker, one that passes the 7,000 hertz and above, and so it looks like this. I'm going to send that signal to that speaker, the little one. And then I'll build one more filter. This is a band pass, and I want it to look sort of like this. Kind of make sure there's no real gaps here. I'm going to send that one to this speaker, the mid ranges, kind of centered on 2000 hertz. And the last thing that I want to talk about is the Q factor. We have an equation for Q, but we're not going to use it. There are no exercises with it. But Q says, how fast does this roll off? A very steep drop off to 71% of the total voltage or amplitude, or power, whatever. That's called a high Q. It's very steep. If I just had this and it kind of tapered out like this, that would be a low Q. And the Q factor, it'll depend on the electrical characteristics of the filter, and then the speaker itself has its own Q factor, but you kind of know what that is. Q is like a sharp, it gets there fast and gets away from it fast. And So for a low Q, of course, it's going to be very spread out. That's low Q. High Q is a real sharply, well-defined amplitude peak. All right.